In the lecture today, we are going to discuss about um, a little bit of chemistry of life, and we'll establish fundamental or foundational knowledge about what are atoms, what are molecules, what are different kinds of molecules which are relevant to human body or a living system. So matter is anything that has mass and occupies space. It has a physical substance that is made up of the universe. So matter can exist in several different forms, for example, solid, liquid, gas, or plasma. Solids have fixed shape and volume. Liquids have fixed volume, but they take the shape of the container. Gases do not have any fixed shape or volume. They can expand to fill the entire container. And plasma is the high energy state which contains the ionized particles, example stars or lightning. When we talk about composition of matter, we talk in terms of atoms and molecules. So atoms are the smallest substance of matter that retains the property of the element. Say for example, if you talk about hydrogen element, you can talk about hydrogen atom, and the properties of hydrogen atom will actually tell you what are the properties of hydrogen element. So in other words, you can say atom is the smallest particle of an element or smallest representation of an element. Molecules are group of atoms coming together. So if I have to give you an example, oxygen O itself is an atom. But when oxygen combines with itself through a chemical bond and makes O2, it becomes a molecule. What are elements? Whatever you see in the periodic table, they all are elements. Whatever has been described or discovered by scientists till date. Of course, there might be many more that we have not discovered yet, but this is what we have right now. An element is a pure substance that cannot be broken down further into simpler substance by any chemical or physical means. The elements consist of only one type of atom. So hydrogen is purely hydrogen, oxygen is purely oxygen. And they are identified based on their number, which is atomic number. And atomic number kind of represents how many protons are present in that element or in the atom of that element. Majorly carbon, hydrogen, oxygen, um, nitrogen make the bulk of living system. 95 to 96% of living organisms are made up of these four elements. But then there are other elements which are trace elements which are also very important. For example, iron, zinc, copper, iodine. All these also play a very crucial role in the functioning of human body or other living systems. Each element has its own unique chemical properties. They have their own unique chemical symbol. For example, H means hydrogen, O means oxygen, C means carbon, and they are all organized in this periodic table. If you look at each of these columns, you know that the elements placed in one column, they have similar properties. An atom is the smallest unit of an element that retains the property of the element, and it's the building block of matter. You can combine atoms and make several different things, and that's what we're going to talk about in upcoming lectures. The atom in its core has a nucleus, and the nucleus contains protons and neutrons. Protons are positively charged and neutrons are neutral. And around this core, the nucleus, are electrons that are constantly spinning, and these electrons have negative charge. And these electrons are mainly responsible for the chemical properties of an atom. If an atom is able to lose or gain an electron, that actually defines how they are going to react with other atoms or other elements. So in short, there are three main subatomic particles of an atom, which are proton, neutron, and electrons. Atoms are defined by their atomic number, which is the number of protons in the nucleus of an atom. Sum total of protons and neutrons in the nucleus of an atom gives us the atomic mass. Atoms form bonds to make molecules, and these molecules are where the story begins. For example, carbon and oxygen make carbon dioxide, and carbon and hydrogen can make methane. And atoms of the same element that have the same atomic number, which means they have the same number of protons, can have different atomic masses because they would have different number of neutrons in their nucleus. These are called isotopes. So these are actually isotopes of each other. For example, what you can see here with carbon, you have carbon 12, carbon 13, and carbon 14. They all have 6 protons in their nucleus, so their atomic number is 6, but their atomic masses are different because they have different number of neutrons. Having extra neutrons makes these atoms very unstable sometimes, so they can become radioactive. So the radioactive isotopes decay over time and they emit radiations. These radiations can be low level radiations or high level radiations, and they have several applications in the field of biology, in diagnostics as well as treatment. As mentioned earlier, molecules are formed when 2 or more atoms combine. If you have a combination of 2 atoms, you call the molecule diatomic, and polyatomic molecules are when you have more than 2 atoms involved. Organic molecules are essentially carbon containing molecules, and they are associated with living organisms. So they are mainly found in living things or living beings. Inorganic molecules are not typically carbon containing, and they are also found in nature, in rocks, in minerals, in oceans, essentially outside of living bodies. So molecules are formed when 2 or more atoms combine chemically. These chemical bonding can be of several different types. First type that we are discussing right now is the ionic bonding. The ionic bonding is when one atom transfers its electron to attain a more stable state. So the goal of any atom is to complete its outermost shell. Here you can see that this second to last shell of sodium is full, but in the last shell it has 1 electron. And on the other side, where chlorine has 7 electrons and is only 1 short of being complete. So sodium would like to give its electron to chlorine, and it will have outermost shell complete, and chlorine will also have outermost shell complete. This kind of bonding leads to the formation of sodium chloride. In another situation where you have covalent bonding, covalent means both the atoms involved have the equal tendency or equal valency, and therefore instead of completely transferring electron from one atom to another, they prefer sharing their electrons. So if they share these electrons, they would have 1, 2, 3, 4, 5, 6, 7, 8, and the other nitrogen will also have 8 electrons out of sharing. Therefore, having 8 and 8 satisfies the needs of both the nitrogen atoms involved, and this kind of bonding is called the covalent bonding. So today we'll talk about molecules which are inorganic in nature, which are not essentially associated with living organisms, but they are also found in nature. First very interesting molecule without which life would never exist is water. In water you have 2 atoms of hydrogen and 1 atom of oxygen, and its chemical formula is H2O. Now oxygen is electronegative. it has the tendency of pulling the shared electrons towards itself, so it becomes slightly negative and hydrogen becomes slightly positive. Because of this difference in positive and negative poles in the molecule of water, we say molecule of water is polar. Because of this polarity, here you can see the oxygen of first water molecule would be able to attract the hydrogen of next water molecule, which has slight positive charge. So this kind of attraction leads to hydrogen bonding. This hydrogen bonding is interesting as well as important because it gives different properties to water and ice. In ice, you can see that there is a definite arrangement of these hydrogen bonds, and there is a geometrical structure between the molecules of water. Therefore, there are several huge empty spaces, which is why the density of ice is low. Whereas in liquid water, you see that there are no empty spaces, or not as big empty spaces as in ice. Molecules are moving all over and they are tightly packed. That's why the density of water is higher. And you know that ice is lighter than water because in your drinks you have seen that ice floats on the surface of your drink. Water has high heat capacity. It can absorb and retain large amount of heat in itself. Therefore, it actually acts as a temperature buffer in our body. It helps in regulating the temperature of our body. For example, when we are hot, it helps in cooling down, and when we are cold, it stabilizes or warms the internal temperature of our body, so that chemical reactions or biological reactions still go on unperturbed inside our body. Water is also a universal solvent. There are so many things that get dissolved in water, including nutrients, gases, waste products. Thus, water is able to act as a medium for several chemical reactions to carry on. Cohesion and adhesion are two very interesting properties of a water molecule. Cohesion is the attraction between the molecules of water itself, and adhesion is the attraction of water with other substances. For example, if water is in a glass container, then the attraction between water molecules and glass is an adhesive force. Because of the cohesive forces among the molecules of water itself, they end up making a thin film on its surface. And here you can see that the insect is able to walk on the surface of water because the water has created a thin film on its surface because of surface tension. In the other video, you can see that if you touch a droplet of a liquid, it gets sucked into a small capillary which is made of glass. That is because the molecule of liquid or water has attraction for the glass substance because of the adhesive forces. pH is a word that most of you must have heard extensively and is repeatedly used in chemistry. Basically, pH gives you the idea about the acidity or alkalinity of a solution. So we will say that a pH of 7 is the midpoint of pH scale. So pure water has a neutral pH and the value is 7. Any number below 7 is acidic and any number above 7 is basic. As we go down the scale and as the number keep getting smaller, it says that the hydrogen ion concentration of these liquid is high. And as we go towards number 14, we say that the hydrogen ion concentration of these solutions is very low and they are basic in nature. In layman's term, acidic material are sour in taste and basic material are soapy in texture. So all the acidic solutions would have a pH lower than 7 and all basic solutions would have a pH of higher than 7 and neutral would have a pH of 7. So if you go towards this direction, you will see that the sourness of solution is increasing. Milk is less sour than banana, and tomato is more sour than banana, and vinegar is more sour than tomato. Lemon are more sour. Acid in your stomach are more sour than lemon, and ultimately you have hydrochloric acid, which is very, very acidic or sour. And as we go towards the right on the scale, we see that everything is becoming more and more soapy. You have soap, then you have ammonia solution, you have bleach, you have drain cleaner, and ultimately you have sodium hydroxide, which is very soapy and even corrosive in nature. So to recap all this information, acidic solutions have very high concentration of hydrogen ion and their pH value is less than 7. They are sour in taste, example hydrochloric acid and vinegar. Biologically, you can find acid in your stomach, and it's important because it kills microorganisms that you can ingest with your food, and it also helps in activating several different enzymes in your stomach. If the level of acid in your blood fluctuates, it can be a serious condition because then several enzymes would fail to work at a low pH. Basic solutions have high concentration of hydroxide ion, or you can say they have low concentration of H positive or hydrogen ion. Their pH values are greater than 7. They are bitter in taste and they are soapy in texture. An example are sodium hydroxide, and when dissolved in water, it produces ions like sodium and hydroxide ion. Biologically, the liver produces bile, which is basic in nature, and this basic environment is again very crucial for several biochemical reactions in your body. Buffers are very important for chemical reactions and in a chemistry lab, but as far as the scope of biology goes, all you need to know is buffer are solutions which resist change in pH, and they are important because our body is very sensitive to pH. Our enzymes inside our body are very sensitive to pH, and it becomes important that we maintain a narrow range of normal pH inside our body. So blood is very good at maintaining the pH level by converting carbon dioxide into the acid, the carbonic acid, or converting carbonic acid or bicarbonates back into carbon dioxide gas. The internal environment inside the cell, which is the cytoplasm, is also good at stabilizing the pH so that normal enzymatic reactions can take place inside the cell. In our digestive system, buffer neutralizes the acidic pH of stomach so that enzymes can work on our food bolus and help us digest it better.